In this tutorial, we're going to take a look at the solutions to a test review on the derivatives of sinusoidal functions. And so in the first part, there's four multiple choice. Number one says if h of x equals sine x, then we're asked to find h prime of x. So the derivative of sine is cosine. So this would actually be the cosine of x. And if you look in the, now there's a negative cos x, so wrong sign here. The derivative of sine certainly isn't sine. So we don't actually have a correct answer. So E would be the best answer for question number one. In number two, f of x equals 4 cos 5x minus 7. So we're asked to find f prime of x. So if we're going to differentiate this, the derivative, so we'd start with the 4 times. The derivative of cosine is negative sine. So we have a negative sine 5x, and then you multiply that by the derivative of the 5x, which would be, that's why I left a little space here, which would be a 5. Now this is all multiplied, so probably best to put a set of brackets around this. And the of course, negative 7 is a constant, so its derivative is 0. So in the beginning here we have 4 times negative 5, so that would be negative 20. And then sine 5x. So that's why A is the correct answer. Question number 3. If f of x equals sine kx, where k is a constant, then what's the derivative? So the derivative of sine x is negative cos x. Sorry, the derivative of sine x is cos x. So we would write cos kx. And then we multiply it by the derivative of kx, which would be k. So we would stick k in front here. And so that is answer A, k cos kx. And last multiple choice, number 4. If we're differentiating negative 3 cos 6x, so we start with the negative 3 times, and maybe we'll put this in a set of brackets. The derivative of cosine is negative sine, so we'd have a negative sine of 6x, and we multiply that by the derivative of the 6x. So maybe I'll erase my little negative here, and so it would be negative 6 sine 6x. Now multiplying this negative 3 and negative 6 would give us 18, so it would be 18 sine 6x. Which is answer C here, 18 sine 6x. Part number 2, we're asked to differentiate, well, 4 different functions. There's a D as well on the top of the next page. In A, we're asked to differentiate q of x equals 2x to the 4th sine 5x. So this is a product because we've got this power of x function and the sine x function multiplied, so we use product rule. So let's start by differentiating the 2x to the 4th. So the 4 comes down in front. 4 times 2 is 8. Reduce the exponent by 1. And so that's the derivative of the first function times the second, undifferentiated. Plus, now we do the opposite. So we start with the first function times the derivative of the sine 5x, which would be cos 5x times, and the derivative of 5x is 5. That's why I stick this 5 in front. And so the beginning, this part's fine. There's nothing to simplify there, but I would multiply the 5 by the 2x to the 4th, giving us 10x to the 4th cos 5x. For B, h of t is sine cubed 6t. And so that cube means it's actually sine 6t all cubed. And so this is actually going to be chain rule because it isn't just x to the power, or t to the power 3 we're differentiating. It's a function of t to the power of 3. So I start with differentiating the outside function. So the 3 comes down in front, and it's the inside sine 6t to the power of 3 minus 1 is 2. And then we multiply by the derivative of what's in here, which would be cos 6t times 6, 6 being the derivative of the 6t. And so I'll multiply the 6 by the 3 to give it 18. And then I got these two different sine and cosine functions, so it really doesn't matter which you write first. So I wrote the sine one first. I'm again putting the 2 back here. It's sine squared 6t, which is the same as sine of 6t squared. This is just a more accepted form, and then times cos 6t on the end. In C, we have a quotient, the y equals sine 2x over cos 9x, so I'm going to use quotient rule. So quotient rule starts with the bottom function times the derivative of the top, which would be this derivative of sine 2x would be cos 2x times the derivative of 2x is a 2. and then minus the top function times the derivative of the bottom. So the derivative of cos 9x would be negative sine 9x multiplied by 9, 9 being the derivative of 9x. And that's all over the denominator squared, so the cos 9x gets squared here. So I would write my 2 in front here, and then now it doesn't matter whether you go cos 2x or cos 9x or the 9x one first, it really doesn't matter. And a negative times a negative is a positive, that's why this is going to be plus, and I'll stick my 9 in front. And again, sine 2x first, sine 9x second, or the other way around. If you want to put the 9x here and the 2x here, it doesn't matter. And in the denominator, cos 9x squared, again, we write that as cos squared 9x. That's what that means up there. In question D for number 1, we're given this f of m function. It's 5m squared minus sine of m squared minus 5 cos cubed m to the 4th. And so we've got several parts here. So before I get into differentiating though, I'm just going to write this cos cubed function as cos of m to the 4th, and that means it's cubed. So that's just rewriting this function. Differentiation doesn't start till this line. So the derivative of 5m squared, power rule of 2 comes down and multiplies by the 5 to give you 10m. Power 1, because 2 minus 1 would be a 1 here. Now I'm going to differentiate the sine of m squared function. So the derivative of sine is cosine, so cosine of m squared, and then we multiply that by the derivative of the m squared, which would be 2m. And it's a good idea not to write the times 2m here, because some people might look at it and think that, oh, I've got to multiply that 2m by the m squared and write 2m cubed. The whole cosine function is multiplied by 2m, not just what's in here. So that's why it's a good idea to put that 2m right there. So let's just erase that. Now I finished this part, so now I differentiate this, and it's kind of like a chain rule of a chain rule almost, because we've got this cube function, but inside we've got a cos of another function of m. So always start at the outside and work your way in. So the 3 is going to come down and multiply by the 5. I didn't bother to write 15 because I'm trying to show all the steps here. So the 3 comes down, and then it would be the inside function here, the cos of m to the 4th, and then just to the power of 2. Again, I'm differentiating the power of 3 function here, so that's why it's a 2. And then we multiply that by the derivative of what's in here. Well, the derivative of cosine is a negative sine, m to the 4th, and then we have to multiply that by the most inside function, the m to the 4th, which would be 4m cubed. So that's where the 4m cubed comes from. So this whole part right here, is the derivative of this. So it is a bit of a long derivative. So let me just, actually might be simplest just to do that, to delete that. Okay, so now let's just simplify. 10m doesn't need to be simplified. I'll get rid of this multiplication, right? 2m cos m squared. And then on the end here, we've got a negative, well, 5 times 3 times 4 that's 15 times 4 is 60. And this negative here, multiplied by the negative, will be positive. So 60m, and this would be, I'll put my m cubed here. And then we have a cos m to the 4th squared. So again, I'll put the 2 here, cos squared m to the 4th, and then sine m to the 4th in the end. And now, it's okay to leave it in that form. The only thing I did here was I dropped the brackets because you don't really need to have the brackets on. Most people probably would accept either of these last 2 lines. They're really equivalent. The brackets do serve to differentiate between parts a little bit. That's maybe not the greatest word to use here because we're differentiating, but to distinguish between. But either of those would be acceptable. Question number 2 in the second part. We're asked to find the equation of tangent line to y equals 3x squared sine 2x, where x is 3/4 pi, and to write the tangent line in the equation in standard form. So I need to find the slope at this place, so I need to differentiate this. It's a product, so I'm going to use product rule. So I'll start with the derivative of 3x squared, which would be 6x, times the second function, the sine 2x function, and then plus, and now the opposite, the first function, times the derivative of the second. The derivative of sine 2x would be cos 2x, and then times 2 being the derivative of 2x. And the only thing I would simplify from this line to this line is I'll multiply the 2 and the 3x squared together to give you 6x squared. So there's my derivative. I want to find the value of the derivative at this 3/4 pi. So I'm going to substitute 3/4 pi in place of x everywhere. So we substituted here, so it'll be 6 times 3/4 pi, and then here, so sine of 2 times the 3/4 pi, and then here it's going to be squared in the in place of the x here in the end as well. So for a bit of simplifying that goes on here, see 2 goes into 4 twice, and into 6 3 times. And so that 3 times 3 pi is 9 pi, and it's going to be over 2. And then I can, this 2 will divide into the 4 twice. And so I'll have the sine of 3/2 pi, or 3 pi over 2. And then I'm going to square, actually do this, I'm going to square all these. So 3 gets squared, the pi gets squared, the 4 gets squared. So 3 squared is 9, pi squared is pi squared, and 4 squared is 16. And just like here, that 2 is going to go into the 4, leaving a 2 in the denominator. So we're taking the cos of 3 pi over 2 in the end here. Now, so again, lots of simplifying. So first of all, let's go here. 2 goes into this 3 times. And 2 goes in 16 8 times. So 3 times the 9 pi squared is 27 pi squared, and it's over 8. Now the cosine of 3 pi over 2, that is 0. And I guess a couple ways we could do this. Make sure your calculator is in radian mode, of course. So the cosine of 3 pi over 2 is 0. We can also use the unit circle if you're familiar with it. So here's the unit circle I was talking about. I got rid of my scientific calculator here, or graphing calculator. So evaluating the cosine of 3 pi over 2, if you're familiar with this, all these ordered pairs are the sines and cosines of the special angles from 0 around to 2 pi. And so the cosine is the x coordinate, the sine is the y coordinate. So if we want the cosine of 3 pi over 2, we look around the circle for 3 pi over 2, and we find it right here. And so the cosine is the x coordinate. So again, it's 0, just like the calculator showed us too. And also over here, we want to find the sine of 3 pi over 2. So 3 pi over 2, the y coordinate there is -1. So that's how I substitute -1 in place of the sine of 3 pi over 2 there. And of course, if you wanted to reevaluate this, we could go sine 3, want to do it in the calculator. Graphing, regular scientific calculator, doesn't matter. Okay, so there's a -1 as well. So a couple ways you can get that. I'm not going to get rid of that unit circle because I'll need it again in a moment. So 27 pi squared over 8 gets multiplied by 0, so that's gone. And then since this is -1 times the 9 pi over 2, which is -9 pi over 2. So that's the slope of the tangent line. Now, maybe we'll move this over here. We need to find the, now I'm just going to use y minus y1 equals mx minus x1. So I have the slope, okay, that's my slope right there. I have the x coordinate, that's the 3 pi over 4 that we were substituting here, but I need to find what the y coordinate is there. So back to the original function, y equals 3x squared sine 2x. And I'm going to substitute 3 pi over 4 in place of x. Okay, so it's going to go here, squared, and here as well. And so just like over here, actually maybe we'll just delete this and bring it back. This is similar over here when we squared the 3/4 pi. Of course, we got the 9 pi squared over 16. And we're going to multiply by 3. And then this 2 goes into the 4, just very similar to over here. And we end up 2 goes into 4 twice. So we're taking the sine of 3 pi over 2. And just like on the well, I guess I don't really need my unit circle again, because just like the sine of 3 pi over 2 is -1 there, it will be here as well. So that's -1. And then this 3 gets multiplied by the 9 pi squared over 16. So 3 times 9 is 27 pi squared over 16 times the -1. So it's -27 pi squared over 16. So that's my y coordinate. I'm going to fill in here. So that's my y value. That's my slope. And of course, x is 3/4 pi. So double negative here, we take the brackets off, so it's going to be y plus the 27 pi squared over 16, and there's my slope. I'm going to multiply it, expand it, and distribute it into the brackets. So negative 9 pi over 2 times x is negative 9 pi over 2x, and negative times negative is positive. 9 pi times 3 pi would be 27 pi squared, and 2 times 4 is 8. Now we want to go in standard form, so I'm going to bring all the terms to one side. And so from this line to this line, I just brought this term over to the left and the 27 pi squared over 8 as well. Now, what I did to this, kind of looking ahead, because, let's see here, this is going to be a like term of this. So what I did was, seeing that this is a 16, I'm going to multiply this by 2 to get a common denominator. So when I brought this over, that's going to be 27 pi squared over 16. Sorry, 27 times 2 is 54 pi squared over 16. And of course, negative when we bring it over to the other side. So those are actually like terms, have a common denominator now, so we can subtract them. And then, so I have my y here, and then the 9 pi over 2x term, and then 27 pi squared over 16 minus 54 pi squared over 16 will be negative 27 pi squared over 16. And if we want to put it in standard form, since the denominator here is, well, the least common denominator of 2 and 16 is 16, so I'm going to multiply everything by 16. So if I multiply the y by 16, this by 16, and that term as well, so 16 times y is 16y, and then I can actually do this. So 2 goes into 16 8 times, and so 8 times the 9 pi is 72 pi x, and then the 16s divide out, so I get negative 27 pi squared. So that's an equation in standard form. I guess if you really want to be technical, you might want to, somebody might want to, like, if you really want to be, a lot of people are like the standard form to be x term first, y term second, and then the constant at the end. So that would certainly be acceptable too. And so that's our equation in standard form. Flipping over to question 3. And in question 3, the population of a certain species of rough grouse in area can be modeled by the equation g of t equals 3000 sine 0.2 pi t plus 650. G of t is the population and t is the number of years after 2016. So g is population, t is the time in years. And in A it says find, or asked to find, a function that represents the rate at which the gross population is changing. So the rate at which it's changing would be the derivative function. So the derivative of this, so we would start with the 300, and derivative sine is cosine, so we would write cos 0.2 pi t, and then multiply that by the derivative of what's in here. Now, the derivative of 0.2 pi t would be 0.2 pi, the constant multiplied by the t. And if we multiply 300 by 0.2, we get 60, so this would be 60 pi cos 0.2 pi t. In part B, you're asked what are the maximum and minimum populations of this species of bird prior to the year 2025. Now, that's kind of an arbitrary value. If we get into C here, how long the population cycle, it actually extends, well, almost a full cycle. So it's not really important, the 2025. So for this function we're given, the plus 650 is the vertical translation. So the g equals 650 would be the average population. And since the amplitude is 300, the population varies 300 above and 300 below the average. So 300 above would be 950, 300 below 650 would be 350. So it's varying between 350 and 900 gross. C asks, what's the length of time for one complete population cycle? And this value here we can use to find the time. The period would be 2 pi divided by this constant here. So 2 pi divided by 0.2 pi, the pi's divide out, and 2 divided by 0.2, because I could demonstrate that with my calculator, I suppose. 2 divided by 0.2 gives you 10. So it's a 10-year cycle. Now in D it asks what's the rate at 0 years and also halfway through the cycle. So halfway through the cycle would be at 5 years. So at 0 years and rate again, so we want to calculate g of 0 and g of 5. So we're using our derivative function here. So I'm substituting 0 in place of time. So it'll be 60 pi cos 0.2 pi times 0 here. And then similar for the 5. So 0.2 pi times 0 is 0. The cos of 0 is 1. So, and again, I could use the unit circle, I suppose, to show that. So we paste it back in here. The 0 is right here. And again, it's the x-coordinate, so that's why it's 1. So the cos of 0 is 1. So 60 pi times 1 would be 60 pi. We'll get rid of that unit circle. And for 5 years, pi over 2, sorry, 0.2 pi times 5 would be pi. 0.2 times 5 is 1. So we end up with the cos of pi, which, and maybe we'll paste a unit circle back in here again. Pi is over here. The cosine is -1. There's the unit circle there again, value, -1. Again, we could do that as well. So on the graphing calculator, I suppose. 60 pi times -1 is 60. -60 pi gross per year. That's the rate for each one. Question E asks, what do you notice about these two derivative values from D? Explain any similarities. So notice that they are just the opposite of one another, 60 pi and -60 pi. So they are opposite. You should expect that because the original function was a sine function here. And so I didn't graph the exact function, but it's an untranslated horizontally sine function. So we should expect, so we found the rate at 0 years and the rate halfway through the cycle. And if we draw tangents there, we should see that those two are exactly the opposite slope tangents. So we should expect those two rates to be the same except one positive and one negative. The rate it's increasing here is the same as the rate it's decreasing right there. In question number 4, the residential and commercial voltage in Afghanistan can be modeled by a sinusoidal function that ranges from -220 volts to positive 220 volts and has a period of 1/50th of a second. So in A, it asks to create a sinusoidal function that models this behavior. So sinusoidal, you can use cos or sine. You're not told it has to start with a max or a min or in the middle. So you can just make a choice here. So I chose to use sine. So I'm going to let V of t represent the voltage at time t, and t is measured in seconds here. And if it varies from -220 to positive 220, then 220 is the amplitude. Sine, well, what goes here? What's my k value? So I find that value by dividing 2 pi, because that's the period of the untransformed sine or cos function, by the 1/50th of a second. We're told that's the length of a cycle. And so we take the numerator and multiply it by the reciprocal of the denominator to divide rational expressions. So 2 pi times 50 is 100 pi. So there's my k value. So that's a function that models this voltage. In B, it says find a function that represents the rate of change of this voltage. So a rate of change, we would differentiate our voltage function here. So V prime of t. So starting with the 220, the derivative of sine is cos 100 pi t times the derivative of 100 pi t. Well, the 100 pi is just a constant times the t, so it would be, the derivative would be 100 pi. And so simplifying this, 220 times 100 is 22,000, and don't forget your pi, and then the cos 100 pi t. So that's the rate of change function. And in C, you're asked, what is the maximum rate of change of voltage? So we're asked to find a maximum of a rate of change. So one way to do this is using the second derivative. So I'm going to differentiate this V prime to get the V double prime here. So starting with my 22,000 pi, the derivative of cos is negative sine 100 pi t, times again the derivative of 100 pi t would be another 100 pi. So multiplying 22,000 by 100, and I brought my negative out here, gives us 2,200,000. Pi times pi is pi squared, sine 100 pi t. And to find the maximum, we're going to set that equal to 0. So I would divide out this negative 2,200,000 pi squared. So that's why in the next line I just have sine 100 pi t equals 0. Now in order to solve for t, I want to solve for the 100 pi t next. So I would take the 100 pi t would equal the inverse sine of the 0 here. And so the inverse sine of 0 is 0. So 100 pi t would equal 0. And then dividing by 100 pi, we get t is 0. So at time 0, there is a maximum rate of change of voltage. So, well, what is that rate of change? So I'll go back to my rate of change function, and I'll plug 0 in place of time here and here. So it would be 22,000 pi cos 100 pi times 0. Of course, 100 pi times 0 is 0. Cos of 0 is 1. And so 22,000 pi times 1 would be 22,000 pi volts per second. If you want to change that to a decimal, it's about 69,115 volts per second. So that's the highest value of the rate of change, the fastest the voltage is changing. And it should make sense. I said there's more than one way to do it. I was going to show it using the second derivative. You see, this is a cosine function. And so a cosine function, it starts at a maximum, so it should make sense at a time 0 there is a maximum. So if you wanted to rationalize that instead of using the second derivative, well, cos starts at a max, so the time has to be 0, so we can plug 0 in here. Then that works too. And that's the end of the review tutorial.